much. My name is Tibor Balint, and I'm from the Space Technology Mission Directorate. I'm the program executive for the Game Changing Development Program, which is one of the 9 programs within space technology. In this presentation, I will talk to you about 3 things. One of them is a little bit of an overview of space technology. We are a brand new mission directorate, and I'd like to tell you all about what we are doing. Also, I will give a couple of examples what we are doing currently for the International Space Station and what kind of projects we are foreseeing, what we are planning. But it's not limiting to those technologies. We are open to new technologies as well. And finally, we'll close out with telling you about how you can get involved with technology developments, with Space Technology Mission Directorate, and how to feed forward for a potential ISS demonstration mission. So with space technology, we were established about 3 years ago as the Office of the Chief Technologist. We had 2 primary goals. One of them is to provide an agency-wide advocacy for technologies between all the mission directorates. And also we had a specific technology development program when we were developing point design technologies, component systems that again feeds into mission directorate and other needs. And I will tell you more about that. About 3-4 months ago, we became a mission directorate. We split up OCT to 2 parts. One small office remained an advocate for technologies across the agency, and we became the mission directorate responsible for technology development. So it's very similar to what you can see at the Space Science Mission Directorate, when you have SMD developing technologies, flying missions, and Office of the Chief Scientist is providing the agency-wide advocacy for science across the agency. So why do we invest into space technologies? If you look into the past 30-some years, there were over 40 studies pointing to the fact that we need regular investment for new transformative space technologies. And we had a couple of space technology programs. They were coming and going. And we found that currently we don't have this capability available for the agency. We have to establish that. We have to enable a new class of NASA missions that can go beyond low Earth orbit. And we have to provide innovative solutions that can dramatically change the shape of how we're doing space exploration and provide these technologies for NASA and also provide it for the nation. These technologies, we are hoping, will be affordable and reliable, and it can enable future NASA missions. And in addition to work with our stakeholders, like other mission directorates, we also want to open these technologies up and develop these for new markets. We want to enable innovation and also support the emerging aerospace business. In addition to working with all these stakeholders I mentioned, we also want to work with the next generation. We want to work with universities, academia, and bring up students and train them to make sure that we have the next generation of performers coming to NASA and work with us, and also utilize universities as a home for the knowledge base and leverage that environment to provide technology development for us. So in general, we are working with the NASA workforce. We are working with universities, working with academia. We also work with businesses, which includes both large businesses and small businesses. Work with other government agencies, and in a broader sense, we work with the whole aerospace industry. So when you look into space exploration, there are a couple of big challenges that we have to overcome if you want to have these future missions happening. Communication is a big issue. We want to have large data rate, reliable communication back to Earth, especially when you go for large distances. And it's valid for both human missions, when you have to have live videos to interact with astronauts. Also, if you go to distant destinations like the Jovian system and you want to map Europa or other planetary surfaces, you have to send back large volumes of data that we cannot do currently. Navigation is a very important issue. With technology developments, we can pinpoint our location anywhere in the solar system with high accuracy. Radiation mitigation is again one of the top poles. If you want to go to Mars with humans, long duration, multi-year missions, mitigating against the radiation environment is key. Environmental control, life support systems. We heard the presentation yesterday, how important that is, especially when you go farther and farther away from Earth. You have to close the water loop, the air loop, the food loop to take less resources with you and recycle the resources you have. Manufacturing innovation is another emerging field with 3D printing, with new materials, from ceramics to amorphous metals. And we do this already on Earth. We have to bring it up to space and enable our space missions with these technologies. And I will be repeating, when I give you examples, I'm repeating some of the stuff that you heard earlier today and also over the past couple of days. So I'm pointing back to some of those presentations. Power generation and storage. If you want to go to Mars, you need significantly more power than we can generate right now for space missions. Propulsion, we have launch propulsion, in-space propulsion that we have to develop. We want to put more mass into orbit, and we have to deliver these masses to our planetary destinations. Logistics, with increased distances, you have to have more autonomy to allow the systems to work efficiently. And once you get to your destination, for example, you get to Mars with humans, you have to land large masses which are order of a magnitude larger than what we can land currently. So all of these are technology toll poles that we have to address to enable future explorations. So when you look into our portfolio within space technology, we have a couple of guidelines. We have a number of guidelines that we are working with. We adhere to stakeholder-based investment strategies. If you look into key drivers for technologies, we have the space technology roadmaps, which are identified 14 technology areas. We have, similar to the decadal survey, we work with the National Research Council, and they provided a report on what kind of technologies they believe we should invest in. And we have the Strategic Space Technology Investment Plan, the STIP, and that basically combines the list of technologies and priorities of technologies that allows us to pinpoint to the needs that we have to develop. We have a very comprehensive portfolio within space technology. We're covering a full TRL range. We have early stage developments, mid TRL, high TRL, and then we pass it on to mission directorate needs and other national needs. We are developing transformative cross-cutting technologies. We believe that there are different ranges for technology. You can have sustaining, incremental technology developments. Very often, those can be done within mission directorates. And very often it's done because of needs, improving current existing capabilities. But the next step is what's happening beyond that. We have to develop those technologies which can enable the new missions, the new capabilities that we currently don't have. We are trying to focus on those ones. Also, our projects are merit-based when it comes to competition. It means that everybody can apply. Within NASA, the workforce of NASA centers can apply, universities, academia, industry. Even we can have international collaboration, even though we cannot have exchange in funds, but we have collaborations where we can work with everybody. Also, we have structured projects. So it means that our projects have a cost allocation, a schedule allocation, well-defined projects. We don't want to perpetuate the development for decades. For example, for game-changing, we have 2-year projects with the potential to extend for a 3rd year. And after that, we just move on. We have down select gates, we have schedules, and we want to make sure that our technologies are improving. And either by pushing the boundaries, we succeed, or we can fail. But that's okay, because we can have an informed risk on this pushing the boundaries, and we'd rather fail early and move on to a new technology than just drag it on and not to make progress. We also comply with the NASA procedure requirements. So it means that for mid-TRL, we are going by 7120.8, and by high TRL technology demonstration projects, which are flight projects, we are going by 7120.5, and this is very typical for the agency. Also, we try to position NASA to a cutting edge of technology development. So these are the driving principles that we use for space technology. Again, I mentioned to you that we are aligning ourselves with the Strategic Space Technology Investment Plan, and we did a portfolio analysis for our current investments, and we found that 72% of our portfolio, current existing portfolio, is aligned with the core needs identified in the STIP. Also, about 10% of our portfolio is aligned with low TRL technology investment, which feeds into future needs, which are low TRL now, but if you mature it through the technology range, that it can enable new capabilities. And about 18% goes into adjacent technologies. This is a kind of a visual representation of the 9 programs within space technology. And on the left side, you can see the list of the 9 programs, starting with Space Technology Research Grants, NASA Innovative Advanced Concepts, Center Innovation Funds. These are the low TRL programs from TRL 1 to 3. If you go to higher, we have the Game Changing Development Program, where I'm the program executive. We are developing technologies in the 3 to 5 range. We can mature this technology across. We have this internal innovation pipeline, and once we develop it, we pass it on, advance it further, and eventually, at the end, once we do the technology demonstration, small spacecraft technology flight demonstrations, we can pass it on to mission directorate needs, other agency needs. But this is not the only avenue we can develop technologies. It doesn't have to always go through our internal pipeline. We can work with external mission directorates. We can co-fund technology developments. We can pass on from mid-TRL to other mission directorate needs. For example, we are having, as George mentioned, a close collaboration with the Human Exploration Mission Directorate with Advanced Exploration Systems, AES. And what happens is we are developing component technologies. And from game-changing, mid-TRL, we pass these technologies over to AES. They integrate it with their systems. And then once they develop those, they pass it on to HEO needs. On the right side, you can have these bubbles. And the point there is just visually try to represent that in the early stage, we have lots and lots of ideas, but it's low TRL. You try to figure out if these ideas actually make sense. Are they feasible or not? So the funding for those technologies are lower. 100K for phase 1, maybe 2, 3, 4, 500K for the second phase. But once we figure out that these technologies are feasible, we can go to the next stage. And then we down select, we have fewer projects, but they are larger in scope. So in the mid-TRL range, you are ending up, instead of maybe 100 to 500,000, maybe a 500,000 to a million to 5, 10, 15, 20, even maybe up to 40, 50 million dollars. And then once you mature through the mid-TRL range, we call it the valley of death, then you go to the technical demonstration part, and those technologies can be in the 30 to 200 million dollar range, and they are flight demonstration missions. If you want to slice our portfolio slightly differently, there are 3 key areas we are trying to address. We are creating new markets and growing the innovation economy. So these are the kind of a lower TRL. So actually they are not. They are the Flight Opportunities Program, SBIR, and Centennial Challenges. Then we have the pioneering concepts and developing innovation community. So that's the lower TRL. When the Center Innovation Fund is when we give money to all of the 10 NASA centers, and the center chief technologists can decide which are these emerging technologies where they want to invest. NIAC, again, it's a little bit of blue sky, low TRL program when people can come up with ideas and say, why don't we look into it? It makes sense. Let's see if it works or not. And bring it up to maybe TRL 2 or 3. And they have 2 phases in NIAC, phase 1 and phase 2. And then you can mature it through up to 3. At that point, we can pick it up and bring it forward. And the Space Technology Research Grants is working with universities, working with academia, both with graduate students and faculty. And you can have university teams proposing to NASA, either from one university or collaboration with multiple universities. And the third group is the transformative and cross-cutting technology breakthroughs. These are the game-changing, the mid-TRL technology developments, and the 2 flight demonstration programs, the technology demonstration and the small spacecraft technologies. And this is just a snapshot example to show that we have a number of projects within game-changing and technology demonstration, and they feed into mission directorate needs. For example, next generation life support. We are developing components for the next generation life support system, and they feed into the new EVA portable life support system. And then AES is integrating them together, and they make it available to HEO. So I'd like to mention a couple of examples. I'm pointing back to presentations in the past couple of days. Within technology demonstration, which is the highest TRL within space technology, we have the Human Exploration Telerobotics project. And this project has 3 key elements. One of them is smart spheres, and you heard about spheres yesterday, and we put a phone on it, and we worked with the interaction, how to use commercial off-the-shelf technologies in collaboration with spheres. The other one is Robonaut 2. You heard the presentation yesterday, how to work between astronauts and a robot in a collaborative way. And surface telerobotics, and George mentioned that as well, we are doing pretty soon, when astronauts will be driving a rover down on Earth, and it can feed forward to future missions if you go around Mars and try to operate robotic assets down on the ground. From game-changing, from the meteorial, a couple of examples, including 2 projects from our human robotic systems. One of them is the Robonaut legs. Now we have the upper body of the Robonaut. With the legs, once we couple them, we can do EVAs and move around the International Space Station by grappling the handrails and move around and do different tasks that is harder to do for astronauts. Also, we have an exoskeleton. That's a kind of a white exoskeleton you can see over there. We were developing this for multiple uses. One application is on the International Space Station. Astronauts can use it as an exercise machine, or you can measure how the muscles perform during the space flight. Currently what we do is before launch, we measure the muscle performance. After they come back from long duration flight, we measure it again, we compare the difference. With this one, it's a resistance device, you can measure it continuously on the International Space Station, and that provides feedback on astronaut performance and health. But the switch use of this application is down back on Earth. If you are not using the exoskeleton as a resistance device, you can use it in the joints as motors, and you can help people with spinal cord injuries to walk again. So we're working with the Veterans Affairs to make sure that we can transfer this technology for uses down on Earth. Other technology is the slosh experiment. You heard about spheres. The story here is that we have 2 spheres, and we put a tank, a liquid tank inside, and looking at it with the camera, we have a predetermined motion of the spheres, and the fluid starts sloshing inside. We videotape that, and we use the footage from that as a validation database for our computational codes, which feeds forward for propellant tank filling and use in orbit, which is important for future missions when you have large tanks in space and you try to figure out how they behave, what the momentum is, what the dynamics of the sloshing of the fluid inside large fuel tanks. 3D printing demo, you heard about it before. That's coming through the SBIR program, and we are flying it in FY14. And you also heard about the SMD run NICER experiment, which will be launched in 2017. And that has a companion piece developed and co-developed with SMD, and we are doing that. And we are doing that within space technology, and it's called Sextant. And it's an X-ray navigation capability when you're looking at pulsars, and from that you can triangulate your location anywhere in the solar system with high accuracy. So it's a technology demonstration, lower TRL than the NICER X-ray Observatory, but it's a stepping stone towards enabling new capabilities for planetary exploration. So these are the ones we are doing for sure. We have them either on the International Space Station, or we are planning to launch them in the next few years. But we have ideas what else we can do. And I don't want to go through the whole list, but the bottom line is that you can utilize the ISS multiple ways. One of them is you can use your experiments inside the ISS, you can use it outside of the ISS, and also approaching or leaving the ISS. And it can be either for using on the ISS or as a stepping stone to try out technologies for future capabilities that we want to use for exploration. But in general, we will carry on working on the Robonaut 2. And you heard the laser printing demo, and George mentioned that we are looking into a scanner potentially to figure out, how to scan an object and do fast prototyping in orbit. We don't have to get Earth involved with that. And currently, our 3D printing is involved with plastic printing, but we also want to print metals. Now, you cannot do the very popular powder-based 3D printing in orbit because of the zero-G is not facilitating that. So we have to go to a different method. We have to develop that capability, but once we develop it, it can open up new avenues to space exploration. We can demonstrate power systems like fuel cells. And as I mentioned, not only we can use technologies and demonstrate technology in ISS, but also by returning or going towards it. Another example for that is small entry probes. We can try out thermal protection systems on small probes by building them, dropping them back from the International Space Station. They are instrumented, they are measuring the performance of the TPS, and that can provide feedback information for a few future planetary exploration missions. For human robotics, we can also look into augmented reality. You know about Google Glass. Similar to that, the interface between the instruments and the payload between astronauts and the payload is very important. Make it simpler, make it more informative is a next step in this interaction. And so there are many examples across the whole 14 technology areas that we can develop and maybe use the ISS as a stepping stone towards it. So these were the mid and high tier of technologies. And just to show you that we look into earlier stage development as well, for under NIAC, which is tier 1 to 3, we are looking into the next generation of spacesuit. Try to figure out how to make it easier for astronauts to operate in the space environment, the zero-G environment, still protect them. Also, we can look into how to protect them against radiation using magnetic shielding. Does it make sense to have an active shielding or not? What will it require? Still low TRL. I don't know if it's going to pan out or not. There are possibilities, and we have just look into it and mature the technology further. For SBIR, you heard the example of the 3D printing. We have additive manufacturing, space communications, deployable space systems, and we are investing across the whole, across the full TRL range, and we are working with small businesses in collaboration with NASA and bring these technologies up through multiple stages from first to third in SBIR. So what are the funding opportunities for working with space technology? One possibility is working through solicitations. We are releasing these solicitations on a regular basis, and anybody can apply. Mission directorates, other government agencies, industry, academia. And if you go to our website, you can get information on that. But the same way as you heard in the morning from the Science Mission Directorate, we also go through NSPIRES. And if you sign up with NSPIRES, every time we release a new solicitation, you can get an email from NSPIRES saying, hey, solicitation came out from space technology, and you can find more information out about that. But in general, we'd like to have a kind of a typical cadence for our solicitations. And an example is shown here. SBIR, in the beginning of the fiscal year, in the first quarter, we release our call. Of course, all of these are dependent on funding availability. All of this is dependent on continuing resolution or not, just to know how much money we have. But in general, given that everything is working out fine, SBIR typically releases the solicitation first quarter. The Space Technology Research Grants, it has 3 elements for fellowships and early career faculty. We do it in the first quarter. And then for early stage innovation, we do it in the second quarter. As I mentioned, fellowships is for graduate students, master and PhD students. For early career faculty, it's for university faculty positions. And also for early stage innovation is teams, university teams proposing technologies. NIAC, the phase 1 is released in the first quarter, and phase 2 in the second quarter. And the center innovation funds are sent to the NASA centers in the first quarter, and then the center chief technologists distribute them among the centers. And for game changing, again, we are a large program. We have different theme areas where we want to have investments. Our projects are 2 years long, and when they are over, we start to pick new content for our program. And the new content is based on either directed projects or competed projects. And if it's a competed, then we come out with a solicitation, typically between the first and the third quarter. We don't want to wait too long, because we have to evaluate them and select them and then obligate the money by the end of fiscal year. So that's why at the beginning of the year we try to do this. But we have flexibility to release them whenever the need comes up, when we identify a technology that we want to develop further. So in general, we develop new hardware for all needs within the agency, outside the agency. Within game-changing technology, we go through this valley of death. We already know that it's likely going to work, so we have to build engineering models. We have to test them. We have to make sure that they are up to about tier 5, and we can pass it on to technology demonstration. And once we demonstrate them, then we can pass it on to mission directorate needs. So we also work with other government agencies. A couple of examples. For green propellant, we work with AFRL. For solar cells, we have co-funding with NOAA, and the idea there is for solar cells, they would really like to see a solar cell in the Lagrangian point between the sun and Earth. So in that case, we can have early prediction of space weather from the sun, and that can provide us information for both scientific and engineering needs. Also, we work with the Army on Sword, which is a cheap launch vehicle. We can launch about 25 kilograms to a 750 kilometer orbit, which can enable small satellite revolution. And this will be very cheap, about $1.5 million, $2 million per launch. So it will be very good to launch multiple small spacecraft. And we also work with DARPA on this next generation humanoid challenge. The challenge is coming up in December. Multiple teams, international teams are building humanoid robots, and they have to go through a set of exercises to demonstrate that these robots are very capable. And as I mentioned, exoskeleton, working with Veterans Affairs to make sure that we can translate this technology we developed for future use.
I'm just wondering, can you describe how these collaborations evolve? Is it project specific, so someone wins a project from the Air Force, and then in a later stage now somebody becomes interested and the collaboration develops, or is it something that develops in the beginning?
It can work multiple ways.
Okay.
It can be all directional. So sometimes we have a technology, we are looking for partnerships, we find out that another government agency is working on something similar. We try to figure out how to pool resources and leverage that. Sometimes they approach us with the development. Sometimes from ground up we start this, sometimes we jump in. So there are no recipe that this is the only way we can do it. We have full flexibility. When we see that there is a need, we can strengthen our relations, we can leverage our resources. It can happen anytime. So the bottom line is the last slide I have, that we are working together to innovate. We try to address all of the needs of the agency and the nation and support an emerging space technology environment. So if you have any questions, I will try to answer them. This is my last slide. Thank you. Questions? We're ready for lunch. I think everything was answered pretty much the past couple of days, so it's kind of a recapping and tying back to it. But if you have a question, do you have a question? Sorry. No, sorry. No questions? Excellent. So I think lunch is coming up, and thank you very much.